What we're going to look at here in this video is what's called the scalar triple product. Now this is basically going to be a combination of both our scalar product and our vector product together, where what we're going to look at is multiplying two vectors and then using it to calculate a scalar. Now the fundamentals of this come from calculating the volume of a parallelepiped and being able to use the vector product to calculate a property of the parallelepiped, which we can then use to calculate the overall volume itself. So let's imagine in 3D space we define a parallelepiped, which is going to be a space bounded by three pairs of parallel planes. So it's a three-dimensional shape that looks something along these lines here. Now we know that this is going to be the same as a prism. And in order to calculate the volume, what we can do is multiply the area of one plane in the pair by the perpendicular distance between the planes. So what we can do is, if you look at this here, we could imagine calculating what would be the equivalent of the base, so this plane made by the B and the C, and then multiply it by the perpendicular height here in terms of A, such that we're able to get the entire volume of the parallelepiped itself. Now, from fundamental maths and fundamental shapes theorem, we know the volume of this is equal to area of the base times the height. Prisms, that's exactly what we do for the volume. Area of the base times the height. Now, this base here in this shape is defined using the B and the C vectors. So what we can do in order to calculate the area of the shape, so that's what our A is going to be the equivalent to, is we can do the cross product, the vector product of B and C, and then take the magnitude of that. So that will give us the size of this plane here on the bottom. What we then have to do is multiply that by the height. Now if we focus on this right angled triangle here, what we're going to do is we'll take the right angled triangle. We know there's our height h, there's our theta, so the angle that is at this point here between the vector and the diagonal between one corner and the other on the base of our parallelepiped. We've got our height there, and we've got the vector A going along that way there. Now using basic trigonometry, what we can do is figure out that h, our height, is equal to the magnitude of A cos theta. So we've now got an expression for h, we've now got an expression for A. What we can then do is combine them and say, right, so what that means is the volume of our parallelepiped is given by the magnitude of the cross product of B and C, so B cross C, times the magnitude of A cos theta. Now, magnitude of A cross theta dotted with this, what that's the equivalent of doing is A dot B cross C. So that there's the equivalent of combining our vector product and our scalar product to give us the volume of this three-dimensional parallelepiped in 3D space. And that there is how we calculate it. Now, key thing to note here is the overall final operation is the scalar product. So this will give us a scalar as an answer, i.e. it will tell us the size of our volume. You might look at it and think, well, there's a vector product in there, and we know the solution of a vector product is a vector, and that can't be used to describe a volume. But because of that scalar product being the final step that we take there, give us a scalar overall, and that will then tell us the volume that we're after. Now, there's a couple of key things that we need to make sure we're aware of when we're working with our triple scalar product. A couple of key properties, again, that we need to take into account when we're doing any calculation involving this. So first thing is that any three pairs of planes could be used to find the volume. So we used the B cross C to give us the base and did A dot B cross C. We could have also used the C cross A to give us the area of that plane and then done the dot product with B to give us the overall volume. Or we could have used A cross B to give us the area of that plane and then done the dot product with C in order to be able to calculate the volume from that. It doesn't matter which pair we use to define our base, if you like. As long as we define it using two non-parallel vectors, we've always got a plane there. Big point here, as I mentioned before, it's a scalar. It's not a vector. We can't have a volume which is a vector. Second thing here is similarly to what we've got up here, A dot B cross C is the equivalent of A cross B dot C. So we get the same answer regardless of which order we take it in terms of that. And overall, as I've mentioned as well, we call this the triple scalar product. And it's often denoted using this notation here. So the square brackets, A, B, C. So there's the name of your three vectors, and the square brackets give it away. Key point here to note is that if any of the vectors A, B, or C are 0, then a triple scalar product is A dot B bracket B cross C equals 0. So a triple scalar product in that case is going to be 0. If any two of the three vectors are parallel, then again A dot B cross C equals 0. If we have a pair of parallel vectors, remember we cannot use them to define a plane. That means a plane doesn't exist in that direction, so we can't find the volume of the overall shape. So a triple scalar product is 0. Now, since A dot B is also a scalar, if we were to write A dot B in a bracket cross C, this has no meaning. A dot B gives us a scalar, and a scalar doing the vector product with a vector has no meaning. So the triple scalar product can be written without ambiguity as A dot B cross C. So we can just get rid of the brackets if we want, because we know we have to take the vector product first. In order to do the scalar product, we have to have two vectors, so we have to do the B cross C part first, or the vector product, depending on which two vectors we choose. That has to be done first before we can take the scalar product at that point. These are just some of the key things you have to remember. Now, in order to calculate this, we have to be able to write it in terms of its component form of all three vectors. So let's imagine I'm going to take my three vectors. I'm going to have A being A1, A2, A3. I'm going to take a vector B as being B1, B2, and B3. And I'm going to take a vector C, similarly, being C1, C2, and C3. What I'm going to do is I'm going to start by doing my B cross C. And I'm going to do it the similar way that we've done before. So I'd set it up in a matrix style. So I've got my I, my J, and my K, my plus, minus, plus. I'd then have my B, so my B1, B2, B3, my C1, C2, and C3. And if I was to do that just as I normally would, work everything through, what I'd end up getting is a vector that was given by B2, C3, minus B3, C2. Then I'd have B3, C1, minus B1, C3. And then my final component here would be given by B1, C2, minus B2, C1. What I then do is I do the scalar product of this with A. So then I would do my A dot B cross C. So what that would mean is the scalar product of the A1, A2, A3 with this new vector that we've got. So B2, C3 minus C2, B3, B3, C1 minus B1, C3, and then B1, C2 minus B2, C1. And if we were to do that, we'd just multiply corresponding components together. So what I'd end up getting is A1 times the first element, so A1 times B2, C3 minus C2, B3. I'd then have plus A2 times the second component, so B3, C1 minus B1, C3, and I then have the third one plus A3 times the B1, C2 minus B2, C1. So I'd have it written like that. Now again, that's a heck of a formula to remember, but it does work out quite nicely as to a much simpler way to do it. This one here, what to do is if you take it a negative, similarly to what we did when we looked at defining the vector product, and write it as minus A2 bracket B1 C3 minus C1 B3, what I'm able to do is define this as a matrix where instead of i, j, k being my first row, I've got A1, A2, A3, B1, B2, B3, and C1, C2, C3. And again, above it, I can write the plus, minus, plus again. So I can actually remember it in that fashion, and it makes it a heck of a lot easier than trying to remember this whole formula here. Now, if you remember the formula, great, good on you. I'm certainly not going to stop you. But this here just makes it a lot nicer and easier to remember and work with. Let me show you an example. So let's calculate the volume of the parallelepiped created using the planes defined by the vectors A, B, and C, all three given here. Now remember, volume of the parallelepiped is given by our triple scalar product A dot bracket B cross C. And in this case, we're going to define it using the vector and sticking them into the component form of the matrix that we were talking about previously. So we're going to take it and write it as 1, negative 1, 1. Get them the right way around. 2, 3, and 4. And then 1, negative 1, 4. Put my plus, minus, plus at the top, just to make sure I remember it. And then I just calculate through each of the wee determinants. So I've got 1 times my determinant of 3, 4, negative 1, 4 there. I've then got minus, minus 1. So what I'm actually going to do is just turn it into a plus 1 straight away to begin with. I've then got 1, not negative 1, 4. I've then got plus 1 times the determinant with my 2, 3, 1, negative 1. Now each of the coefficients here are 1, so all I need to do is each wee determinant on its own and then combine the whole spiel together. So this one here, I've got 3 4s, which is 12. Take away 4 times negative 1, so take away negative 4. Plus, and here I've got 2 4s, which is 8. Take away, remember, 1 4, that's just my wee mistake there. Take away 4 there. I've then got plus 2 times negative 1, so negative 2. Take away 1 times 3, take away 3. So what I've then got is I've got 16 plus 4 minus 5. So I've got 15 cubic units. So that there is the volume of the parallelepiped creating using the planes which is defined by those three vectors. Now again, it's important to remember I could have done it any other way. I could have done A cross B with the C being the scalar as well. I could have done B as a scalar with the C cross A. Doesn't matter which way around we did it. We should still get the same answer each time. One thing to point out is that there is a triple vector product, A cross B cross C, but that's just beyond the scope of what we're going to be doing in the advanced higher course. If you want to look at that, go and have a look at some more advanced material, some university work, some early university materials, and push yourself on with that. But this here, triple scalar product, there you go.